The impact of global warming on the world's tallest flowering plant, Eucalyptus regnans, is a pressing concern that cannot be ignored. As temperatures rise and extreme weather events like droughts and heat waves become more frequent, the survival rates of trees globally are being significantly affected. This study delves into how these climatic changes are influencing the carrying capacity of mountain ash forests, which are not only the tallest angiosperms on the planet, but also among the most carbon-rich ecosystems. To understand these dynamics, we analyzed extensive data from a network of silvicultural experiments conducted in southeastern Australia from 1947 to 2000. Our goal was to identify trends in tree mortality rates and the overall carrying capacity of Eucalyptus regnans, while also examining how these trends correlate with variations in climate over time and space. Our findings reveal a concerning trend. Forests located in the warmest areas, with the highest vapor pressure deficits, exhibited the lowest carrying capacities, which further declined as temperatures increased. Specifically, we project that a temperature rise of 3 degrees Celsius by 2080 could lead to a staggering 24% reduction in tree density and carbon stock within these forests, equating to the loss of approximately 240,000 hectares of mature mountain ash forests. Notably, the trees that succumbed to mortality were, on average, only 62% the size of their living counterparts, indicating that suppressed trees are more vulnerable, with climate factors showing no significant impact on this size ratio. These findings have profound implications for forest conservation and management strategies. A reduced carrying capacity could severely hinder global efforts aimed at forest restoration and carbon sequestration, which are critical in combating climate change. Introduction. Forests play a vital role in our ecosystem, acting as one of the largest terrestrial carbon sinks by absorbing about 1/3 of global carbon emissions annually. However, the ongoing changes in climate are jeopardizing the ability of these forests to continue functioning as effective carbon sinks. Reports of increasing tree mortality rates in various regions around the world are becoming more common, a trend that correlates with rising temperatures and intensified drought conditions observed over the past century. As climate change progresses, physiological models predict that tree mortality due to drought will continue to escalate. The primary concern from an ecological standpoint is not merely the increase in tree mortality rates, but rather the changes in the forest's carrying capacity, which dictates how much carbon a forest can store. If forests transition from being carbon sinks to carbon sources due to increased mortality and lower densities, the implications for climate change mitigation could be dire. Therefore, establishing a connection between mortality rates and changes in carrying capacity is crucial for predicting how forests will adapt to climate change. In even-aged forests, the concept of carrying capacity can be illustrated by the self-thinning line, which represents the maximum number of trees of a specific average size that can coexist in a given area. This self-thinning phenomenon is a fundamental principle in plant population ecology, resulting from the balance between stand growth and density-dependent mortality. As trees grow larger, they require more resources and space, leading to the suppression and eventual death of smaller trees. Recent research has enhanced our understanding of the mechanisms driving self-thinning, including tree morphology, metabolic rates, and competition for resources. While self-thinning lines can vary based on species and site quality, they have traditionally been viewed as stable over time. However, the rapid changes in climate are challenging this assumption, as many regions are experiencing increased aridity, reduced soil moisture, and heightened vapor pressure deficits. Theoretically, these changes should lead to a decrease in leaf area, reduced photosynthetic capacity, and ultimately a decline in forest carrying capacity. Despite the urgency of this issue, Few studies have investigated how the self-thinning line evolves over time in response to climatic variability, creating a significant knowledge gap in our understanding of forest dynamics. Another critical aspect to consider is how tree mortality is distributed within a stand. Climate change is unlikely to affect all trees uniformly, yet it remains unclear which trees are most susceptible to mortality. Research in mixed-species forests has indicated that larger, taller trees may be at greater risk, while studies in monocultures have consistently shown that smaller, suppressed trees are more vulnerable. This discrepancy highlights the need for further investigation into the factors influencing tree mortality. In this study, we build upon recent advancements in self-thinning modelling to explore changes in carrying capacity and the climatic drivers affecting mountain ash forests. By utilising long-term data spanning 5 decades, we aim to quantify temporal changes in forest carrying capacity, their relationship with climate conditions, and shifts in the relative size of dying trees. Based on our findings, we will also project future changes in forest carbon stocks under various climate warming scenarios. Results. Our analysis indicates that both temperature and mortality rates of mountain ash trees have risen over time. Specifically, temperatures in the study region increased by 0.71 degrees Celsius from 1947 to 2000, with notable year-to-year variability. During the same period, the mortality rates for Eucalyptus regnans, adjusted for tree density and size, increased by 33%. Statistical modelling revealed that higher mean annual temperatures were linked to lower carrying capacities. This relationship held true whether we examined temperature effects across different locations using static self-thinning allometries, or over time with dynamic self-thinning allocations. On average, each additional degree Celsius increase in temperature was associated with a 24.6% rise in mortality rates and a 9% decrease in the carrying capacity of mountain ash stands. Our model predicts that a 3 degree Celsius increase in mean annual temperature will lead to a 24% decline in tree density and carbon content in these forests, aligning with projections from the CSIRO RCP 8.5 scenario for the region by approximately 2080. Discussion. Human activities have driven the Earth's temperature up by nearly 1.5 degrees Celsius since the Industrial Revolution, and this trend is expected to persist. Our predictions indicate that a 3 degrees Celsius rise in temperature could reduce the carrying capacity of Eucalyptus regnans by 24%. The trees that died were consistently smaller than their living counterparts, averaging only 62% of their size, with no significant climate-related effects on this pattern. While numerous studies have examined spatial variations in self-thinning, only a handful have explored temporal variations. The geographical patterns observed suggest that trends in carrying capacity may be influenced by regional climate constraints. In temperature-limited systems, increased carrying capacity may arise from longer growing seasons and higher CO2 concentrations, while forests in warmer, seasonally dry climates face different challenges. Our findings support the notion that as temperatures rise, mountain ash forests are able to sustain fewer trees, highlighting the complex interplay between temperature and vapor pressure deficit in influencing forest dynamics. The implications of our results extend beyond theoretical understanding. They have practical consequences for forest management and conservation strategies. As the carrying capacity of forests declines, the ability of these ecosystems to provide essential services such as carbon storage and water supply is jeopardized. This underscores the urgent need for adaptive management practices that consider the dynamic nature of forest ecosystems in the face of climate change. In conclusion, the the reduction in carrying capacity due to climate warming poses significant challenges for global tree restoration initiatives, which are often viewed as a key strategy for mitigating atmospheric CO2 levels. Our findings suggest that without accounting for changes in carrying capacity, these initiatives may not achieve their intended outcomes. Therefore, it is crucial to integrate climate-sensitive, self-thinning models into forest management practices to enhance resilience and ensure the sustainability of these vital ecosystems.